Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. On, and in this tutorial video, we'll go through an older Cambridge International A-Level paper 9701 for this not June but November 2015. This is a paper 4.1, which I believe is either the same as 4.2 or 4.3 for this exam series. I wasn't very sure, but what we know is really that in the older syllabus, there used to be section A and section B. We're not going to pay so much attention to that because I'm doing a question by question tutorial. So realistically speaking, I'll only be going through questions that are relevant to the current new syllabus, which have been revamped ever since 2016 onwards. So be careful when you do all the past year papers, yeah? In this first question, we have calcium. Calcium is a main group metal. It's a group 2. So group 2 metal. We're going to complete electronic configuration for calcium atom. So it's in the 4th row. So it's period 4 chemistry. So this is 1s2, 2s2, 2p6. And then you start off to sodium and magnesium, third period chemistry, so 3s2. And then you go from aluminium all the way to argon. And then you fill in a new row, which is 4s. And you are group 2. You are the second element in the s block on the left side of the periodic table. You are 4s2. And altogether, you have 20 electrons based on this 20 number of protons in the atom. When you have a +2 oxidation number, you have a calcium 2 plus ion. So you know calcium atom have lost 2 electrons. And you're going to lose from this 4s orbital. So you're going to end up with 3s2 and 3p6. This is the same as an argon, which is a noble gas electronic configuration. Although this is an ion with still 20 protons, because you have just lost 2 electrons. You have 2 extra protons than electrons. You are positively charged now. This next question, this is part of AS Group 2 chemistry, obviously. You want to prepare calcium nitrate. That means you want to make calcium nitrate in an acid-base reaction. So this is going to be your neutralization. So if we think about it, all nitrates are soluble, and you know how to prepare soluble salt from your O-level, GCSE or IGCSE level chemistry. So we got to react this calcium oxide or calcium hydroxide. So calcium hydroxide, which is calcium hydroxide solutions. And then if I react that with, what do I want, nitric acid, so that I will get nitrate. They'll give me calcium nitrate, the formula of which group 2 ion Ca2 plus, nitrate ion NO3 minus. If you look at something what we call the valency, which is the combining power based on these charges, when you do the cross multiply, you're going to get that. That is how many of those ions you have. This is one of that, and you have 2 of that NO3 minus. You're going to end up with Ca, bracket NO3 twice, and you will get water. This is part of neutralization, right? So we're going to balance every single equation we write. 2 nitrate comes from 2 nitric acid, and we're going to have 2 hydrogens, so we're going to have 4 hydrogens, therefore 2 water molecule there. The next bit of this question, this is about thermal decomposition. You're going to decompose this anhydrous calcium nitrate. Anhydrous means no water of crystallization. So this white solid that you see, identify this white solid. When you decompose nitrate, just in general, a group 2 nitrate has M2 plus 2 nitrate ion like that. And then they will decompose to MO, which is M2 plus and O2 minus, group 2 oxide. You're going to get 2 NO2 gas that comes from the nitrate. And then to balance your equations, when you get oxygen gas, you have to get half of it because you already have 1. And 2 times 2 is 4, plus 1 is 5. You have 6 oxygen atoms. So you cannot have oxygen atom that exists as molecule. So I have half of that. This is a brown gas. This is a colorless gas. When you see this brown gas, you're supposed to test for this colorless gas with a glowing splint that will relight. So this white solid is not going to be the gases. Instead, because we started from calcium nitrate, we are going to get calcium oxide. So the white solid is calcium oxide. They didn't ask for name, they didn't ask for formula. If you write down the formula, it has to be the correct one. So Ca2 plus O2 minus. As you can imagine, the valency when you do the crisscross, it has to be the simplest whole number ratio. So there's 1 and 1. So you can imagine 1 of that Ca2 plus cancel out the charge minus 2 of that Ca2 plus. suggest another observation for this reaction. So besides leaving you a white solid, this is actually a white solid as well, giving you another white solid. What else do you see? Earlier I mentioned about the brown gas. So you know, NO2 is brown, so a brown gas is observed. Or you say brown gas is seen or is observed, that one should be all right. You cannot see a colorless gas. Please do not write you see a colorless gas. The next bit is a common essay. This happened to be lower mark than I expected it to be because they already provided you the trend. So in the older syllabus, they don't use the new syllabus type, so they use the Roman numeral. You can probably think about this as just group 2 like this in your new syllabus. Okay, always have a look in your specification, especially when you do all the past year papers. The ease of thermal decomposition. How easy is it to decompose? It becomes harder to decompose because it becomes less easy to decompose. So what we can say is down group 2, there are more filled electron shells. So there are more filled electron shells. And what does this have to do? So we can say the ionic radius increases. The ionic radius of the M2 plus, because all the group 2 they form they exist as M2 plus cations in their group 2 nitrates. That will increase, they will get bigger, but still the same charge, but still plus 2 charge. So overall charge density would increase because overall charge density would decrease going down group 2 because your charge is the same, charge over size, but your size is getting bigger. Charge is the same divided by size getting bigger, so your charge density of M2 plus decreases, and therefore we can say the M2 plus become less polarizing. So the cations are polarizing on the NO3 minus, so the NO covalent bond become less weakened, so it's not as weakened as much, therefore more difficult to decompose or more difficult to break. That is why the temperature of decomposition will be higher, but they're not asking on temperature required. They're asking you on how easy is it to decompose, because it's become much more difficult to decompose, so how easy it is would decrease down group 2. This next bit is actually A2 energetics. So this is part of advanced energetics, building upon what you have learned from AS. There is something to do with the standard conditions, the theta there, and then hydration and the standard conditions. So one of the mark would be under standard conditions there. So what do we know about hydration? Hydration is basically things like Na plus gas plus a large amount of water, and then you get Na plus aqueous. But it doesn't just, apply to cations. You can also get hydration of anions, such as Cl minus gas plus aqueous. They're going to get Cl minus aqueous. These are just in terms of the equations I know. These are hydration of your Cl minus. This is hydration of your Na plus cation there. So let me just move that aside. So there's your Na plus cations. Hydration will always be exothermic, never endothermic. If you think about what is happening around the Na plus ions, around the cations, you will have the electronegative oxygen, and this will be delta negative oxygen, delta plus like that, and then you're surrounded by delta negative oxygen of the water molecule. So this is what you call ion dipole bond. Ion from the cations or the anions, dipole, they come from the delta plus delta minus of water molecule. You form ion dipole bond, whereas there's no interaction between the gaseous ions because they're so far apart. One of the assumptions for ideal gases, if you want to think of them as ideal gases, that is. Okay, so what is meant by this definition then? So delta H hydration is going to be the enthalpy change for a certain process. So it's the enthalpy change when 1 mole of gaseous ion, it has to be 1 mole because it's in kilojoule per mole. Per mole of what? Per mole of the gaseous ions. I don't say cations, I don't say anions, because it applies for both cations and also anions. Dissolve in a large amount of water or dissolve in a huge excess of water. And this is you can say really to give infinitely dilute solution if you want to. And I don't think that's too important there, but then we have to really then specify under standard conditions as part of that requirement in that definitions. So standard condition will be 29 at Kelvin, 1 atm pressure. The next bit is basically a calculation question. You are asked to find lattice enthalpy, and we are given hydration enthalpy as well as enthalpy of solution. So solution is got nothing to do with hydration. It's just the enthalpy change when you dissolve 1 mole of the substance in a large amount of water to give infinitely dilute solutions under standard conditions. Again, they look very similar, but here this is 1 mole of the substance. Here hydration is 1 mole of the gaseous ion. So what do we have if we write one equation for the enthalpy of solutions? So this is a solid plus aqueous, and when you dissolve in water, all nitrates are soluble in water. So you know about all nitrates are soluble in water from solubility rules back when you were doing much simpler chemistry. I'm going to relate this to gaseous ions because there's the relationship with hydration enthalpy definition. So going from the solid to the gas, actually that one is the other way around. Forming 1 mole of the ionic solid from its gaseous ions, that thing is going to be lattice enthalpy. And this lattice enthalpy is going to be whatever I want to find. This is enthalpy of solution, and this is minus 19 kilojoule per mole. The gas hydrates into the calcium 2 plus cation. There is 1 of these, but there is 2 of that, whereas this enthalpy of hydration is for hydrating 1 mole of NO3 minus. So I need to do 2 times minus 314 there. If I press that onto the calculator, minus 314 times 2, I get minus 628 kilojoule per mole. And this thing here is hydration of calcium 2 plus, and this is going to be minus 1650. I should really clarify that this thing here was 2 times hydration of NO3 minus, and this is equal to that, which is equal to minus 628. In AS chemistry, you have learned about the use of Hess law. Hess law says that the enthalpy change of a reaction does not depend on the pathway you take. So you can take a direct path or an indirect path, the enthalpy change will be the same. So what I'm going to do now is I'm going to go this way. So this is the direct path. So what I can say is minus 19 will be equal to going the opposite. So that is minus the lattice, because the lattice was defined as forming 1 mole of the ionic solid from its gaseous ions. So here I'm going opposite that. So there's minus lattice plus the 1650. Again, that is minus 1650 going the same way. So it's adding with that. Always use bracket because you never know if you will make any mistake. Now they want the lattice enthalpy. I'm going to move the lattice enthalpy to the left hand side, and then I move the minus 19 to this side, I get plus 19. This is minus lattice become positive lattice. This is going to become minus 1650. It's going to become minus 628. Now you're ready to just press your calculator, and you get minus 2259. The first thing you notice is you get a negative answer. You are forming 1 mole of the ionic solid from its gaseous ions. So you're not breaking anything. You're just forming 1 mole of the ionic solid. It is always going to be exothermic based on that definition, sign, value, and unit. Common things to look out for. Last bit of this question, 12-mark question. So this is about comparing the hydration enthalpy of Ba2 plus versus the Ca2 plus. So the hydration enthalpy of Ba2 plus is less exothermic, so you are forming weaker ion dipole bond. So if you think about ion dipole bond, so you are forming the bond between the ions and the dipole. Both of them are dissolved in water, so there's got nothing to do with the dipole. Everything has got to do with the ion. This is to do with the charge density of the ions. So what we can say is, for 2 marks, what we can say first of all is Ba2 plus has a bigger ionic radius, or is much bigger compared to Ca2 plus. But then we must also talk about the size. So bigger ionic radius than Ca2 plus. So that's the size. Both have +2 charge. So then we have to talk about charge density. So charge density is charge over size. So charge density of Ba2 plus is lower than the charge density of that of calcium 2 plus. That refer to the charge density of calcium 2 plus. So therefore Ba2 plus will form weaker ion dipole bond. Ion dipole bond will be weaker with the water, with water molecules when hydrated. And as such, since you are not breaking anything, as you are just bringing the gaseous ions together, surrounded by water, by a large amount of water. So the weaker your ion dipole bond, as I did mention earlier, the weaker your ion dipole bond between the water molecule, which is polar, and your cations, the less exothermic, because forming bond will release energy. Forming bond is going to be exothermic. So form weaker ion dipole bond with water molecules, so therefore, well, basically that's it really. I don't really have to repeat the question. Since I already started, I might as well say that it's just less exothermic. Okay, and that's the end of that 12-mark question. Very nice and easy start to this first question. In this second question, we are asked to complete the table to show the number of unpaired electrons. So unpaired electrons, they even bolded it for you. So make sure you know how to, write down electronic configurations. So we know that this is S1 and S2. SU are the S block element. If I just draw one orbital, because S orbital, you only have one orbital in the S subshell. So this is when you pair them up. So there is 0 unpaired electrons and there's 1 unpaired electrons. When you come to aluminium will have S2 P1, silicon is S2 P2. Well, basically it's 3 to be honest. Of course, there are some other bits before that, like the 1s2, 2s2, 2p6, but I'm just focusing on the important one. So there's 3p3, 3s2. Well, I'm sick and tired of writing the s. You can assume that the s is full now. So blah blah blah, and then 3p2, blah blah blah, 3p3, blah blah blah, 3p4, blah blah blah, 3p5. And now you have fully filled your p orbital. So 1, 2, 3, 4, 5, 6. This is the noble gases. Fully fill out the shell, including the fully filled s orbital, the 3s orbital. There is no unpaired electrons or whatnot. When it comes to aluminium, so if I just draw a partition here so that we are not confused. So I'm not drawing in terms of energy. I'm not saying that this is lower in energy than that. Be very careful, yeah? I just want a bit more space. So this is 3p1 because there's only 1 electrons in the p orbital, whereas this is 3p2, and then it's really a bad idea for me to keep on drawing it because you might interpret it as difference in energy. I'm just going to show you 1, 2, and 3 because when you come to p, this is group 15. Group 15 would have 3 electrons in the p orbital because this is very famous versus the group 16 where you have to pair them up like this, and this is your famous paired electrons repel more than unpaired electrons in your AS first ionization energy assay. So for this group 16p4, you only have 2 unpaired electrons there, and then for chlorine, you put 1 more there to pair them up. You only have 1 unpaired electrons for chlorine, and it decreases to no unpaired electrons at all when everything gets paired up for the noble gases. This is quite easy, 3 marks. You need to be careful to score the best you can if you want to do well for paper 4. Always read the questions, always think back on your AS chemistry. This next bit is also AS level chemistry. This is the reactions of 2 period 3 chlorides with water. So we know that SiCl4 reacts with water. There is hydrolysis. The same thing with PCl5. Okay, they're asking for observations. I'm just going to write an equation first. That will not be acceptable as an answer, but in order to think about what actually happened, I'm going to write an equation so that I can see what happened. You will see that there's plural there because of observations. So you cannot just write 1 observation because they're asking for plural, and for that 3 marks, better be safe than sorry, I guess. Probably not. Probably it's 1, and then somehow 1 mark there. Don't know. Maybe not. Gotta balance your equation, obviously. SiCl4 has 4 chlorines, so I'm putting in the 4 Cl there. 4 hydrogens, you need 2 H2O like that. When you have PCl5, when you add that with water, you'll know from a lot of my topical playlists involving these chlorides of period 3. This is phosphorus plus 5. When you get the acid, you're gonna get phosphoric 5 acid. Because you're not doing a redox reaction, you must still get phosphorus plus 5. There's PO4 3 minus, H plus because for the acid. So I don't mean oxide, I mean phosphoric 5 acid. So when you combine 1 and 3 of them, of course, you know about how formula works. So you need 3 of that H plus, and you need 1 of that P of 4, 3 minus. You are going to get H3 P of 4. But of course, the equation is not balanced. The only way you can balance it is if you actually produce HCl as well. And also we have to get how many phosphorus. So phosphorus is fine, but we need 5 HCl. And having said that, we need 8 hydrogen, which is 4 H2O. That's how the 4 oxygen come from. And this equation is balanced. They're asking for observations rather than equations, so be very careful. You don't get marks for writing down equations, but by writing down equations, I can see SiO2 is insoluble in water. It's a component of white sand, so I get a white solid form, or you can say white precipitate forms. You also get a steamy white film, as this reaction is very, very exothermic. You're just breaking covalent bonds. You're forming a lot more covalent bonds. You're forming a lot more covalent bond, therefore it is very exothermic. You get steamy white film. What else can we say about the second one? You also get very exothermic reaction forming, so that is steamy white fumes. The thing is H3PO4 can dissolve in water to give you phosphoric 5 acid, and therefore you can say a colorless solution, but I mean PCl5 is a colorless liquid to begin with, so you know steamy white film should probably be enough. In both of these cases, you're producing strong acid. Here you're producing 2 strong acids. Some of them can dissolve in water. Obviously, you're going to get pH2, pH1. Both of them are very strong acid. You know, pH1 will be correct as well. pH2 will be okay. pH3 is probably a bit too high for such strong acid. They want you to write an equation for SiCl4 and H2O here. I already written the equation before, so I am just going to copy paste it into the space given there. Whatever you do, make sure you balance your equations. Do not write any equations without it being balanced. This is surprisingly low for these 7-mark questions in this A-level paper. But anyway, they can ask you anything from AS syllabus as well, so make sure you know your AS stuff. In this next question number 3, we have transition element. So what's the definition of a transition element? As you know from the syllabus, it forms compounds. Where it has, actually it forms compounds or ions where it has incompletely filled d orbitals. So if you have completely filled d orbitals, then it can't be considered a transition element. If you have partially filled d orbital, then it will be transition element. If you have totally 0 electrons in your d orbitals, then it's also not going to be transition element. So you cannot have something which is completely empty in the d orbitals. You can have something where the d orbitals are completely filled. Those will not be defined as transition element. Only when you have partially filled or you have incompletely filled d orbitals, then you can call it transition element. I've used this word incompletely filled. If you use the term partially filled, that will be perfectly acceptable as well, because they mean the same thing. The next bit, name the type of bonding that occurs between ligand and a transition element. So they will form a complex. If you know how to define what is meant by a complex as the syllabus required, you will know that the name of the bond is called dative covalent bond, where both the electrons in the covalent bond come only from one atom. This one has another name. It is also known as coordinate bonding. I stick with this dative covalent bond, but because it's stated in the syllabus that they could use coordinate bonding, so question can describe coordinate bonding, and you will be expected to say that they are the same thing as dative covalent bond and be able to define them the same way. In the following question, which of the following species can act as a ligand? Definition of a ligand. So it have lone pairs. It have lone pairs of what? Lone pairs of electrons. And what does the lone pair of electrons do? They will form dative covalent bond. So they are the one with the electrons, and they will donate both the electrons in the covalent bond. And what do they donate to? They donate it to metal center, which could be atom or ion. Now what we have here is NO3 minus. So can it act as a ligand or not? Complete the table by placing a tick in the appropriate column to indicate whether it can act as a ligand or not. So it's not like a tick or cross, it's just a tick. If it can act as a ligand, put a tick. If it cannot act as a ligand, put a tick here. So you have to have a tick for every single line. That's the thing that's confusing about this question. You do not put a cross because they say put a tick in the appropriate column, whether it can or cannot act as a ligand. Well, let's see about BF3 first. BF3, from your AS case study on shape of molecule, 3 bond pairs. And then you get 0 lone pairs. You have 0 lone pairs of electrons. How can you even act as a ligand when you don't even have the electrons to form the dative covalent bond to begin with? This one is trigonoplanar, 120 degree obviously from your shape of molecule. But there's the very mere idea that it has 0 lone pairs, it cannot act as a ligand obviously. This next one, this is 2 amine there. So this is ethane 1,2 diamine. So this is the common EN ligand. So there's the EN ligand there. It is a bidentate ligand. A bidentate ligand because one molecule of that ligand can form 2 dative covalent bonds, as you have these 1 and 2 lone pair sites that can form 2 dative covalent bonds per single ligand. So it can act as a ligand there. NH4+, despite how it looks very much like ammonia, but this is called ammonium. Ammonium is an ion, is also in the AS under dative covalent bond. How does it look like? This is ammonia, trigonal pyramidal with a lone pair, 107.5 degree. But then when you pick up another H+, it's going to go to 109.5 degree tetrahedral, as dative covalent bond is also a sigma covalent bond. So 1, 2, 3, and 4 sigma covalent bonds, and you have 4 bond pair and 0 lone pair. They repel equally the bond pairs, giving you tetrahedral 109.5. Having said that, you will have 0 lone pair, 0 lone pairs. So you already used up your lone pair for picking up a H+, therefore this thing cannot act as a ligand. Ammonia can act as a ligand because you still have the lone pair. Ammonium cannot act as a ligand because no more lone pair there. How about this NO3-? This one looks a bit tricky, but if you know how to draw display formula, when oxygen forms single covalent bond, it has a negative charge, just like hydroxide, right? This is oxygen forming single bond, it has a negative charge. We know it's NO3-, I've got -2 there because nitrogen, when nitrogen form 3 covalent bond is uncharged. When nitrogen form 1, 2, 3, and 4 covalent bond, it must have a plus charge. Nitrogen here, 1, 2, 3, and 4 covalent bond, it must have a plus charge. This oxygen doesn't have any charge because it formed 2 covalent bonds. This is how the structure of NO3- looks like, and you should be able to think of this just like carbonate as well. 120 degree, this is 3 bond pairs and 0 lone pair around nitrogen. In the AS syllabus, candidates should be able to describe the shape of molecules and ions, including ions, analogous. Analogous means similar to whatever is in the syllabus. This is the ones that are in the syllabus. This is similar to the ones that are in the syllabus. You are expected to know the shape as well. So NO3- does have lone pair. Where are the lone pair? Not on the nitrogen, but on the oxygen. So there are more than 1 lone pair there. I've just shown you 1 lone pair there. The mere fact that you have lone pair, it can act as a ligand. Part C, so the very last bit of this question, this 9-mark question. So we have manganese ions that can show similar chemical properties to those of copper-2. So copper-2 is your case study. As you know, reaction with hydroxide, reaction with ammonia, what else? Reaction with ammonia, hydroxide, and chloride as well. So what we have here is use this information and the data booklet, suggest the formula of the manganese species formed in each of the reactions. When they say the data booklet, they're really talking about reactivity studies, especially for this H2O2, you can get redox reactions. So you have to think about something called E0. So this is E-ox versus E-red. And then you need to think about the overall reactions, which is the E-cell. When you just deal with these OH-, usually we are talking about precipitation reaction, something that all level, GCSE or IGCSE level student we have heard of, as most metal hydroxides are going to be are going to be insoluble. So this is going to be precipitation. As you know, all the transition metals ions, they will precipitate out with hydroxide. This is manganese plus 2. So when they precipitate out, you're going to get Mn, 2 plus, and then OH minus, 2 of them. Precipitation reactions, you're probably expected to be able to write the equation for it as well. So aqueous ions from the sodium hydroxide come together, they give you a solid. This is the classic equation for any sort of precipitation. Balanced atom, balanced charges, show the symbol. Aqueous and aqueous, solution and solution come together to give you a precipitate. And the next one, well, I guess like if they say behave just like copper 2, if you want, you can put down the one with H2O, 4 of them, where you replace 2 water molecule with OH minus and the charge cancel out. So I guess this one, or you can write MnOH twice, this with 2 hydroxide, and H2O, not 6, because you only replace 2 out of the 6 water, so there are 4 water. That should be okay as well, just like copper 2 plus chemistry. With the concentrated HCl, if you have copper 2 plus, you will end up with CuCl4, 2 minus, as that one is plus 2, and you have minus 1, and then you have 4 of that, minus 1 chloride, overall is 2 minus. So what are you going to get here? MnCl4, 2 minus as well. This is just going to be your classic ligand exchange. If you don't like the word ligand exchange, you can probably use the word ligand substitution. So spell that out properly. Ligand substitution, don't have much space here. So I guess ligand exchange, or you can write ligand substitution reaction. The very last thing, I'm pretty sure that there is some sort of redox reactions, but to determine what product you will get eventually, we have to look at the data booklet. Just give me a minute to open up my data booklet. So if you look at H2O2 in the data booklet, of course, in your real paper 4 these days, your new syllabus, your new 2022 exams would be having the data booklet, the E0 whatever values, they'll be provided in the question paper itself. So this is the 2015 paper, so we still have those data booklet as a separate document. So if I look at the H2O2, we can be thinking about this Mn2 plus as manganese plus 2. So do you want to go lower oxidation number or higher oxidation number? If you go lower, the manganese 2 plus will be reduced to manganese metal. That means this one is acting as a reducing agent. If it acts as a reducing agent, it will behave as oxidized reducing agent. Then we're looking at this getting itself oxidized. We're looking for H2O2 on the right side of the E0 equation. So I can find H2O2 in front. That will be plus 1.77 volt, where the H2O2 gets reduced. But to have H2O2 getting oxidized, you have to look for H2O2 on the right hand side. So to have H2O2 on the right hand side, meaning to say the H2O2 act as reducing agent, I do not really see that. I do not really see oh yeah, there is. Okay, so there are 2. Let me see if I can find some space there. Let me just move this one up there, I guess. No, that doesn't work. Is this okay? No, that's not okay. Okay, never mind. Let me just remove that equation there. I guess I don't really need that. So let's have a look at some of these redox things. If I have H2O2 plus 2H plus 2 electrons going to 2H2O, this is plus 1.77 volt. And then I have one where the H2O2 is on the right hand side, O2 plus 2H plus 2 electrons, and again I get H2O2 on the right hand side. This one is plus 0.68 volt. If you look at something that involved the Mn2 plus in the equations, you're looking for Mn2 plus on the right as well as on the left. If I have one where the Mn2 plus is, well, there is a lot of the Mn2 plus on the right hand side. So something, and then Mn2 plus on the right hand side. You can have 3 plus going to 2 plus, which is plus 1.49 volt. You can have MnO4 minus, no, that doesn't. MnO4 minus going to Mn2 plus is plus 1.52 volt. And try to look for Mn2 plus on the left hand side now. If I have Mn2 plus on the left hand side, So what would that be? I'm just saying we are playing around with stuff, right? If I have Mn2 plus on the right hand side, I have plus 1.49 volt, I have plus 1.52 volt from the data booklet, yeah, from the data booklet. If I have Mn2 plus on the left hand side, so that will undergo reduction, they will gain electrons, and they will give you the Mn metal. That thing in the data booklet show minus 1.18. Now you got to compare this with this, yeah? So if the H2O2 act as oxidizing agent, then this is going to go higher oxidation number. So if this is getting oxidized, we are looking at Mn2 plus on the left hand side, which is this and that. If this act as oxidizing agent, this itself will get reduced. And if this get reduced, we are looking at H2O2 on the left hand side because they undergo reduction. Now this is plus 1.77. Plus 1.77 is bigger. It is more positive than this. If this is your E red, because they undergo reduction, it is more positive than your E ox. So H2O2 will react with Mn2 plus if this act as oxidizing agent, because itself will get reduced, because this is E red, so it will act as oxidizing agent. Whereas if we look at the other way around, if this act as reducing agent, then this becomes your E red, and this becomes your E ox, where the H2O2 is on the other side, E ox. And this thing, the E red is less positive than this, plus 0.68 volt. This and this is not going to work. H2O2 will not act as reducing agent for Mn2 plus. Cannot reduce Mn2 plus. If you compare this E naught value, this is less positive than that. But it can oxidize Mn2 plus aqueous. What are the possibilities? Both of them are going to be more positive than this H2O2 getting reduced itself. So have a look in the data booklet. You can get the products that contain manganese, plus 1.49 volt. That one just now was Mn2 plus on the right hand side, so that is going to Mn3 plus. So you can say Mn3 plus aqueous, or it could be the one that give you plus 1.52 volt. That was the one that give you MnO4 minus, I guess. Hang on, does that make sense? Because if that is your E red, then that is more positive than your E ox, then it could happen. And if this get oxidized, it could give you this or this. So both of these are acceptable. By using the data booklet, the E naught value, this is probably the hardest one to think about. That is your redox type of reaction there. And that's it really for these 5-mark questions. And this is the end of that 9-mark transition metal question. In this question number 4, we have this halogenoalkane. So this is a tertiary halogenoalkane. The carbon with the chlorine is bonded to 3 other carbons, tertiary halogenoalkane. And this reacts to sodium hydroxide. And this is a nucleophilic substitution reaction. So nucleophilic substitution means it is a hydrolysis, using aqueous NaOH. So that means in water, hydrolysis. If you use it in ethanol, you're more likely to produce alkene instead of a nucleophilic substitution. It will be a elimination. Show the mechanism. Even though this is an A2 paper 4, they can ask you anything from AS. This mechanism is a tertiary halogenoalkane. So I'm drawing a skeletal. If you want, you can draw a display, I guess. Carbon chlorine. Not really a full display, but a partially display, kind of like structural formula. So this is delta minus chlorine, delta plus carbon. The first step that will happen, so step 1, you will do heterolytic fission. Heterolytic fission is a term stated in the AS syllabus. This is slow, this is rate determining step, and you will get a tertiary carbocation. Make sure your carbon is bonded to carbon. This is what you call a tertiary carbocation. Intermediate. It's good to label as part of your mechanism, and you will learn, you will get better at it once you start to label some stuff as you go along. After that, from here to here is the second step. This is going to be the fast step, and this is where the hydroxide will just attack the poor electrons, rich attack poor electrons. Then you're just gonna get OH like that. So even though I show the hydroxide attacking like from the back, it really doesn't matter. It doesn't really attack from the back because this is carbocation ions. This carbon is trigonal planar. So what actually happened is you have a trigonal planar plane like this, and it's not actually attacking from the back or anything. There is empty orbital above and below the plane because it's trigonal planar 120 degree carbon sp2 hybridized. So that means your hydroxide from the lone pair of the hydroxide can attack from the top, or the hydroxide can attack from the bottom of the plane with equal chances. Not that your final product is chiral center, is optically active, but in the case where these three groups are different, then you can get the potential chirality that will come from carbon being bonded to 4 different groups, and then you will get a racemic mixture as a result of this carbocation intermediate trigonal planar geometry, equal chances of being attacked by the nucleophile from the top and bottom of the plane. You will get a racemic mixture which will not be optically active even though you have a chiral center, but you don't have a chiral center there, so there's not much point talking about that. That's the end of that 3-mark mechanism question. Now we have a graph kind of thing here because this is actually part of a longer question on rate of reaction. You use a large excess of sodium hydroxide. If you use a large excess of sodium hydroxide, we can say the concentration of the sodium hydroxide is roughly constant. And not changing when you use a large excess of it. So what is actually changing then? So only the tertiary halogenal alkane changes. But we don't know the order of reaction with respect to the tertiary halogenal alkane. So this is why we have a graph of this tertiary halogenal alkane plotted against time. So the initial concentration means at time equal to 0. What is the original concentration? It's not exactly a 0.60. This is 0.58. Am I correct? Yeah, because it's 0.52, 54, 56, 0.58 mole per dm cube there. Usually this kind of question involves drawing a tangent, that is a tangent at t equal to 0 to work out the initial rate at time equal to 0. But we're going to have to read through the question. What do they want? They say it is first order with respect to this tertiary halogenal alkane concentration. What is meant by... Oh, I thought they actually asked for what is meant by first order. So the order of reaction is defined as... Order of reaction is not asked here, but order of reaction is defined as the power to which you must raise the concentration to in the rate equation. So to get first order from the graph, what is meant by half-life? They want half-life. I did talk about it earlier. That they didn't want the order, they want the half-life. So half-life is the time taken for the initial concentration to fall to half its value. Time taken for the initial concentration to fall to half its value. Now calculate the half-life for this reaction. Show all your working. Very typical of this type of question in paper 5 these days, but it could also come out in paper 4 as well. So they want construction lines, so more than one. They want half-life, they don't want initial rate. So 0.58 divided by 2, I get 0.29. So 0.29 is going to be there. So there's my construction lines. And then I use my ruler and then show going downward like that. So my ruler is not perfect, but it's supposed to be somewhere in between there. If you could follow that, it should come exactly in between there. So it's exactly in between 40 and 60. So that is 50. So that is 50 from 0 to 50. So the half-life, the first half-life, because you cannot just do one half-life, you have to get at least 2 half-life in order to show if they are constant for first order reaction. So when you do 0.29 further divided by 2, you're going to get 0.145. So this is 0.15. So this is a bit tricky. Well, not that bad actually on my diagram. So that is where my line comes to. So the second half-life is the time taken for this blue concentration to fall to half its value. So the time taken is from here from here 50 to 90, this 90, 90, how am I going to read this actually? So if that is 90, then there's 92, 94, 96, 98. So there's 98 seconds. But of course, the second half-life is going to be 98 minus 50 because it's not all the way from 0. It's from this blue color mark here. So 98 minus 50, I get 48 seconds. You will see that within experimental errors, this is not like half the value. This is not like double the value. This is very close to the first half-life. This is called the second half-life, which is 48 seconds. Okay, so I already shown construction lines. So what I do really next is to just, write down some stuff. So the first half-life is that. The second half-life is that. So what can I conclude? My half-life, so more than one, my half-life are constant within experimental error. So therefore, it is first order with respect to these concentrations I'm changing, which is the tertiary halogenal alkanes in these questions. Now, next one, what would be the effect? What would be the effect on the half-life if I double my initial concentration of halogenal alkane? Well, what we know about the half-life stated in the syllabus, candidates should be able to state that the half-life for a first-order reaction is constant. So what is meant by constant first-order reactions? It is governed by this relationship, which is ln2 over the rate constant. Of course, it's stated in the syllabus as 0.69 divided by rate constant. ln2 is just natural logarithm. ln2 is 0.69 something. And this bottom thing is your rate constant, which will remain constant at constant temperature. There are no concentration terms in there. So it doesn't matter what happened to the concentration. A first-order reaction will not be affected when the concentration of the halogen alkane changes. The next question, you want to use the graph to determine the rate of reaction at 80 seconds. It's a curve, so you need to draw a tangent at 80 seconds. That's the only way you can get the gradient. Tangent at 80 seconds. So 80 seconds is going to be here. So here it is, 80 seconds. So I'm going to draw a tangent. Let me use a different color. Let me use red color. Is that good? Nope, that is not very good at all. That is not a good tangent at all. So just give me a minute. Let me try, and that is not a good tangent at all. That is not too bad, as you could see. Okay, so that connects. Is that all right? So that looks alright-ish as a line. So gradient at this tangent might not be the most perfect, but you want it to be a tangent kind of like only touching the surface. You could probably get away with this one, like a bit lower, like this, like this, like this, like this, but it wouldn't change that much compared to the poorer version I did earlier. So you get a right angle triangle now. So your change of the x-axis from 0 all the way to, what do you have here? This is going to be 140, 150 is there. So this is 145, is it 150? Hang on, just give me a minute. So this thing halfway in between, so this is 150. So you have 1, 2, 3, 4, 5. So 142, 144, 146. So there must be 146 seconds. And what do I have on the y-axis? A lot easier, 0.40, 0.42. So 0.42 minus 0, your change in y over your change in x. 0.42 minus 0, this is mole per dm cube. And at the bottom, I have 150 minus 0, this is second. So on top, I have mole per dm cube. At the bottom, I have second. So my unit is going to be mole per dm cube divided by second. So I got to show all my working, right? So I'm showing all my working. And just press 0.42 divided by 150 on the calculator. I get 2.8 times 10 to the minus 3. Do not forget to show your units. There's mole per dm cube per second. So just putting in the final answer now. And mole per dm cube divided by second. The next thing we are told that this comes down to this rate equation. So calculate the value and give the unit for the rate constant. Pretty stingy of them to give only 1 mark, but then K equal to, rate divided by the concentration of the tertiary halogen alkane, which is basically this thing here. So we have the rate, which is 2.8 times 10 to the minus 3. And the unit there is going to be mole per dm cube per second. Do we have the concentrations for these halogen alkanes? Well, let's have a look at the question earlier. Not really, apart from this initial information, 0.58 mole per dm cube, 0.58 mole per dm cube. Okay, so K then, this is mole per dm cube. So that is the unit of the concentration. Concentration unit 1, concentration unit 1. So 2.8 times 10 to the minus 3 divided by 0.58. I get rate constant of 0.8276 times 10 to the minus 3. That is quite a lot of significant figure, considering that this was only 2 significant figure and this was 2 significant figure. I need to think about what is appropriate number of significant figure, and this is second minus 1. And my final answer is just that, and keep putting in the values there in the space given. That's the end of that 9-mark question on rate of reaction. So in this question number 5, we have X, which is a metallic element. So if X is a metallic element, we're talking about metal and also metal ions, and we have to come up with a drawing for this system to investigate or to measure the standard electrode potential. Standard electrode potential, E0, as given in the data booklet. Whether it is given in the question paper itself or in a separate data booklet, you will know that they are measured relative to the standard hydrogen electrode. So in order to measure that value, you have to show the standard hydrogen electrode, which could be drawn on the left or on the right. It does not matter, because the direction of electron flow depends on the sign of the electrode potential anyway. So if I just put in my standard hydrogen electrodes on the left hand side, again, it does not matter where you put the standard hydrogen electrode. This is going to be H2 gas at 1 atm pressure, because we are talking about standard condition, and this is also at 298 Kelvin. So this one is dipped in a solution, and this solution contains 1.00 mole per dm cube of H plus concentration, and I could use HCl for instance if I want to, but not H2SO4, because 1.00 mole per dm cube H2SO4 will give you 2 times H plus ions. You want the H plus ion to be 1.00 mole per dm cube. You don't want the you want the H plus ion to be 1.00 mole per dm cube essentially. Like I said, HCl is okay, HNO3 is okay. What's the other one? H2SO4 is not okay because you will not have 1.00 mole per dm cube H plus. So what I have there is not conducting, because non-metal does not conduct electricity. So what I need is a platinum electrode. This is your conducting electrode, and this is connected to a voltmeter that can measure your electrode. No. It will measure your potential difference. I better get the word right, okay? So when they measure your potential difference, they will measure it in volt. And this thing on the other side, we have a metal and a metal ion. So what we have is the metal as the electrode itself. So if I just write down not M, but they say X is the metallic element, so X is the metal itself. So that is the metal electrode, and metal can conduct electricity in the solid state as a result of your giant metallic structure, and you have delocalized valence electrons and whatnot. So what else do you have? You have X2 plus aqueous. Do not forget, this is 1.00 mole per dm cube of this X2 plus. So I'm just going to have to write down exactly what I'm trying to say here. 1.00 mole per dm cube of this X2 plus aqueous. And your circuit is not complete, so they will not be able to conduct any electricity until you add in this thing called a salt bridge. So on your one side, you have the standard hydrogen electrode remember to label the electrodes, and on the other side you have metal and the metal ions in solution. So this metal ion in solution and the non-metal ion in solution have to be of standard concentration under standard conditions, so 1.00 mole per dm cube. Specify the temperature, specify the pressure, as these are gases coming in. A voltmeter to measure the potential difference, which in this case is relative to the standard hydrogen electrode. That's why it's called the standard electrode potential for this metal and the metal ion system, for that 4 marks there. Well, actually, it could be about 5-mark question. Actually, if you didn't write down the standard conditions there, you're supposed to write down the conditions here. So these are the plural there. So basically, to be standard, we are talking about 298 Kelvin, 1 atm pressure. Do not forget that those are from energetics. Now you're talking about solutions and electrochemistry. So 1.00 mole per dm cube solution there. State the charge carriers that transfer current through the solution and the wire. So the solutions could conduct electricity because of your electrolyte. Your electrolyte contains free ions there. So that is your free ions. And then the wire is made out of the metal. Well, not this metal per se, but it's made out of metal. Metal wires can conduct electricity. So that's to do with free electrons. As a matter of fact, you could be more exact. It's actually free valence electrons that get delocalized, whereas all the electrons in ions, they are localized in the shell, unlike metals. So it's the free ions that allow you to conduct electricity through the solution. The next we have this question. You have a cell now, so no longer just to measure the reduction potential, but you now have a cell. This is between the metal and the metal ions. And they told you that is E naught is minus 0.40 volt. Because it's negative, negative means it favors oxidation. So we always think about reduction potential, electron potential as reduction potential as electron potential. This is X2 plus 2 electrons going to X like that. And the fact that it is negative 0.40 means it actually favors the left hand side of the equilibrium. It favors the loss of electrons. It favors oxidation. On the other hand, Ag plus electrons giving you Ag. So straight from your data booklet, if you are given this data, plus 0.80 volt mean that this equilibrium favors the right hand side. It favor oxidation. It favor the right hand side of this reduction potential equilibrium. Write an equation, so one equation for the reaction that will take place if the electrodes were connected by a wire. So if this is the positive one, this is going to favor reduction. Therefore, this one is going to be the E rad. It's more positive than this negative one, where this one is going to be the E ox. So if that favor oxidation, so it's going to be X plus Ag plus, but that involves 2 electrons. This involves 1 electron, so we need to multiply this by 2. Then we get 2 Ag plus, 2 electrons and 2 Ag. The 2 electrons on the left will cancel the 2 electrons on the right, as you lose the electrons from X to X2 plus. You lose 2 electrons, and the 2 electrons is gained by the Ag plus, but this one gain only 1 electrons, so you need 2 Ag plus to gain the 2 electrons, so you will get 2 Ag. They are not asking for stat symbols, so this equation is balanced like this when the number of electrons get balanced out there. This next question, when the current was allowed to pass for a period of time, the Ag electrode gained this much mass. So the gain in mass, the increase in mass is due to the silver being deposited. So it's the silver solid being deposited. So we're looking at that half equation which I wrote down earlier. Whereas the electron made of metal X lost 0.67 gram in mass. Okay, calculate the AR of metal X. Well, let's see what is happening. So this Ag plus electrons go to Ag, and then we have X2 plus 2 electrons. Oops, hang on. We started from X actually, and then the X would have lost some mass because they get oxidized. Oxidation happen at the anode, and then reduction, which is gain of electrons, where your mass increases, where you deposit the electrons. Reduction at the cathode. What do they want? They want the identity of X. So if we want the identity of X, we need to think about the number of electrons, obviously. And if I first work out from the silver, because I have this information here, so what can I say? We don't have any information on the current and stuff, but what I can say is the mole of electrons in this setup, the mole of electrons is to the mole of silver is 1:1, because 1 mole of electrons give you 1 mole of Ag. So what I can say is the mole of electrons is equal to the mole of Ag, and this is just the mass of Ag, 1.30 gram, divided by the relative atomic mass, which you need to go to the data booklet. Let me also open up my data booklet. So straight from your predict table, Ag is 107.9. So the mole of electrons is equal to the mole of silver. So 1.30 divided by 107.9. I get 0.012048 mole. And then we know that these electrons, all the electrons are going to go to the other side. So even though this is 1 electron here, you do not multiply by 2, because all the electrons from here come from here. And when we wrote down the equation earlier, actually this one we have lost 2 electrons, the 2 electrons are gained here. So this mole of electrons here, it could be for this 1 electron in this equation, but in the overall equations we could see that that the mole of electron transfer is already in the right ratio. So all the electrons here go to here, so we don't multiply by 2. Be very careful, yeah. All of these electrons go to here, all of it. So therefore we have the mole of X is to the mole of the electrons is going to be 1:2. So the actual mole of X is going to be equal to mass of Mr, mass of AR. So that's going to be the 0.67 gram that you lose from the metal X, divided by the AR of X, that is the mole of the X, divided by the mole of the electrons that get transferred onto the silver plus. So you get 0.012048. So altogether you're going to get half times 0.012048 is equal to 0.67 over AR of X. And hopefully you can then, work out the thing correctly, and you will get AR of X is equal to 0.67 times 2 divided by 0.012048. So just do the math correctly. 0.67 times 2, because you move the 2 up there, and you move this one down there, and I get 111.22. And they don't say how many significant figure we should give our answer to. This was given to 2 significant figure, this was given to 3 significant figure, or we could think of it as 2 decimal place, the usual mass balance that we use in the lab, typical of 2 decimal place. So I would probably not give it to 2 decimal place because there's way too many significant figure. 3 significant figure would have been alright, I guess, given that these were to 3 significant figure as well. So look for something with 111, something give or take. What is that metal there? 111. Something with a 2+ charge. Something with a 2+ charge and 111. That is looking like cadmium. Cadmium is just next to silver actually. So I get 111. That looks like cadmium in the periodic table, just next to silver there. Okay, and that's the end of that 11 marks electrochemistry question. In this next question, we have this boron chemistry. So this compound called diboron, B2H6, can be used as a rocket fuel. You react this BF3 with sodium borohydride. We just need to balance this equation very quickly. You have boron here and you have boron here. So you have 2 borons and another boron here. So it seems like the fluorine substitutes out or replace all the hydrogen. You get NaBF4 and all the... Yep, that is what happened there. And now the hydrogen has replaced the fluorine, but now you get B2H6. So let's think about how we're going to balance this. If I have 1 sodium and 1 sodium like this, doesn't look like it will balance, because 3 fluorine, 4 fluorine So the only way you can think about lowest common multiple, 3 fluorine and 4 fluorine, if you do the lowest common multiple of 3 and 4 is 12. So what we need is really 3 of that there. 3 times 4 is 12. 4 times 3 is 12, so 4 there. And what next? If we have 3 sodium, we must have 3 sodium there. And what next? If we have 4 times 3, which is 12 hydrogen, we must have 2 B2H6. And now what next? 4 boron plus 3 boron is 7 boron. 2 times 2 is 4. 4 plus 3 is 7 boron. This equation is now balanced. Okay. Part B. Primary and secondary alcohols can be formed by reacting carbonyl compounds such as ketones or aldehydes because carboxylic acid cannot be reduced by sodium borohydride. So does not reduce carboxylic acid. To reduce carboxylic acid to primary alcohol, you need lithium aluminium hydride, which is a much stronger reducing agent. So this one can reduce ketone and aldehydes to their corresponding secondary alcohol and also primary alcohol respectively. You're supposed to complete this mechanism for this reaction with hydride ion. H minus has a lone pair on the hydrogen because it's got 2 electrons, it's not H plus. So this is your exact same mechanism as in AS chemistry, nucleophilic addition mechanism. So this is from the lone pair. I label the dipole. Rich in electron would attack the poor in electron. So the first thing that happens is rich attack the poor. Once the rich attack the poor, carbon cannot form 5 covalent bonds. So I have to break this bond here. And I gave the 2 electrons to the oxygen. Then I get O minus with a lone pair on the oxygen. That is called the oxy anion intermediate. Now I formed this bond between carbon and hydrogen. I've got an oxy anion intermediate where the negative charge is on the oxygen. I then add in H plus. H plus has no electron at all. So these 2 electrons on the oxygen, they just attack and pick up a H plus, and now you form an alcohol there for that 3 marks mechanism. Part C, boron is used to synthesize alcohol, so you can make alcohol from alkene. So this is not your usual A-level chemistry. What do we know? The BH2 group from BH3 bond to the least substituted. The least substituted means it has the most hydrogen. The most hydrogen, therefore the least carbon. Substituted with carbon, so the least carbon means the most hydrogen, because the more carbon you have, the lesser is the hydrogen. So if we look at this alkene, the least carbon is this one because it's got 1 hydrogen. This one hasn't got any hydrogen. It is the more substituted one. So that means the BH2 will go here and then the H will go there. That's what they're saying, right? The hydrogen will go here. You see, the hydrogen goes there onto the more substituted carbon because the BH2 add to the least substituted carbon, which is the one with more hydrogen and less carbon. So blah blah blah, and then you replace the BH2 and then it becomes OH as you do oxidation. This square bracket O here refers to oxidizing agent, so you must have some sort of redox that you can oxidize this group and then replace it such that the carbon gain oxygen, and this is called oxidation, gain of oxygen on the carbon. What type of reaction is step 1? You have just gone from alkene, you have just added something across the alkene. They are not looking for mechanism. Do not write mechanism in here because they're asking for the type of reaction as stated in the AS introductory organic chemistry terminology. This is going to be addition type of reaction there. Now this diol Y can be prepared by the same method. So now you want a diene. Diene means 2 times alkene. So 2 times carbon-carbon double bond, which could be used to prepare diol Y. So you could see the OH is here, and you must add onto carbon-carbon double bond. If my carbon-carbon double bond is there, so that means I've added that. And now if I draw another OH here, then I have another H here. So that means my another double bond is there. So I just remove that and I get the double bond. And I could get this, which is the other one. So I get the double bond there and the double bond there, diene, 2 time alkene, 1 2 3 4 5 6. So this is hex 1 2 3 4 hex 2 4 diene, as this is 1 2 3 4 5 6. In fact, you can call this trans, although they are not asking you on cis and trans. So you could draw the cis or the trans, it doesn't matter. You could draw the cis or the trans because they all will give you the diene when you prepare the diol by adding H and OH. This is addition of steam, which is H2O gas, and you need concentrated phosphoric acid catalyst. And you are not going to add steam if your temperature is below 100 degrees Celsius. So usually you need a heat, which is around 300, 400 degrees Celsius, somewhere along that line there. The structure, so you could draw, skeletal or structural or whatnot, but essentially you must have 2 time alkene. So what I'm saying is you could also have this one, which is okay. You could also have this one, which is cis and cis. This one is going to be trans and cis. So these or the trans and the trans, they are okay. How about the cis and the trans? The cis and the trans is going to be the exact same molecule as this, because you could just rotate the molecule. You will see what I mean when you draw the cis and the trans, when you just rotate the molecule there. This next one is a long essay question for 3 marks. Describe the structure and bonding in benzene C6H6. This is as stated in the A2 syllabus. You must be able to do this. What I'm going to do really is I'm going to sketch out a picture, and they never say that you cannot show a simple picture. In fact, you can always show a simple picture to make your idea a bit clearer. So I've just shown that there are p orbitals on each carbon, and these p orbitals can overlap sideways, where the electrons hop around and they get delocalization. So this one is basically this thing here, where you have delocalized electrons. Okay, so what is the structure there? Simple covalent structure. That one is very obvious. It exists as individual single molecule, but they are not asking exactly on that. They are asking on what is happening. Each carbon has 3 bond pairs, because if I draw the cocoon structure, you can see it better. 1 2 3 like this. You have H, 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 and H. You count only the sigma bond. So 1 2 and 3 around each carbon. You have 3 sigma bonds, so 3 bond pairs, and you have 0 lone pair. And then this one will give you 3 bond pair repel equally. 3 bond pairs repel equally. This is your VSEPR. So therefore, trigonal planar geometry. So trigonal planar, 120 degree at each carbon. What else can you comment on this? This is carbon sp2 center. Each carbon has 1 unhybridized orbital, 1 p orbitals, 1 time 2 p orbital on carbon that remains unhybridized. That is the meaning of sp2, because you still have 1 more p orbital that you didn't hybridize, otherwise you will have sp3. And these 1 electrons in the 2p orbital that remain unhybridized, they can overlap sideways. Delocalizing the electrons, and therefore pi electron density. You get a pi electron which are rich in electrons above and below the plane. Pi electron density rich in electrons above and below the planar structure. So it is planar, it's completely flat. Alright, so this is just a sideway representation of things. What else can we say? It's not really, alternating single and double bond, as we know about the idea of delocalization. The electrons does get delocalized around, so they're not fixed like alternating double or single, but really it's like a partial, like 1.5, 1.5, 1.5, 1.5, 1.5, and 1.5 bond that the electrons are always moving around like that. Okay, having said that, the rich in electron density above and below the plane is what makes benzene like to be the rich in electrons, and they will attack the electrophile. But this delocalization provides some sort of stabilization that after it does the initial addition and you lost a double bond there, you will always want to go back to being benzene again. Then you will kick out the H plus. That is the special thing about electrophilic substitution mechanism. You want to go back to being benzene because of the resonance stabilization energy due to the delocalization of electron in the structure and bonding for C6H6 there. In this last bit of the question, this is 1 mark question. So they're saying that in borazine B3N3H6, so instead of C6H6, as you know, boron, carbon, hydrogen. So this is in group 13, 14, and 15. So number of valence electrons, this is 3, 4, and 5. When you have carbon and carbon, you have 4 plus 4, which is 8 electrons. When you have boron and nitrogen, you have 3 plus 5, group 13, and group 15. You also have 8 electrons. They actually look very, very similar. You can see that BN bond is actually shorter. Is it? No, BN bond is longer because single bond is weaker. Single bond is weaker. Weaker covalent bond is going to be longer covalent bond, and this is as stated in the AS syllabus under bonding. Whereas the BN bond is a double bond. The double bond is going to be stronger covalent bond. So stronger covalent bond is actually a shorter covalent bond. Okay, because of the stronger force of attraction between the localized shared pair of electrons and the 2 nuclei. So a shorter bond there. What else? This is what happened in reality. This is what happened in reality. You get somewhere in between. This is exactly the same idea of delocalization like in the C6H6 just now, where we say it's not exactly a single, it's not exactly a double. Instead, it's somewhere in between, somewhere like 1.5 kind of bond. So what we have from this information, you draw the structure, you have delocalization. That is the evidence of delocalization. So this thing here is the evidence of delocalization. So what you cannot do is you cannot draw single and double because of this information there. All of them are of the same length, and they are longer than a double, which means it's weaker than a double, but it's stronger than a single because it's shorter than a single bond. So what I do is I draw boron, nitrogen, boron, nitrogen, boron, nitrogen. Why do I do that? Because of this information alternate around the ring. If we know how to read the question, we know how to interpret it. And then of course what I do is I also have hydrogen, 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 hydrogen. You have lone pairs in the nitrogens and you have empty orbitals in the borons. So what actually happens is you must get a ring structure that represent the delocalization of electrons and not the single and double alternating bond, because even though they say this, they also mentioned that all of them are the same length because of the evidence of delocalization, just like what we had earlier with benzene chemistry. We draw this ring, we therefore draw this ring for borazine C6, not C6, B3N3H6 there. And that's the 1 mark question for the suggest kind of structure. So that's the end of that 10 mark question there. Question 7. So this is about coloring agent. What do we have? We have a phenol-like compound S there. So it's not exactly phenol. It looks like phenol. And it reacts to intermediate T. It reacts to intermediate T made from amine R. So we have to react this with intermediate T. Am I correct? Blah, blah, blah. This one will give you this. What's the difference between this and this? Well, let's have a look. If we have C6, because 6 carbon, we are only given molecular formula, so let's just work this out. So C6 and then 1, 2, 3, and 4 hydrogens. So H4, and then nitrogen, there are 1 nitrogen there, and after nitrogen there's 1 sulfur. So I'm just kind of following this thing on the right hand side there. After 1 sulfur there is 3 and there's 5 oxygen, and then there's 1 sodium. What is the big difference here? The big difference is really on the oxygen. So there is 5 oxygen, there is only 3 oxygen. There is 6 hydrogen there, and there is only 4 hydrogen. What I can think of really is this thing remains the same, the SO3NO. That's why they have shown us the exact same thing, which is this one. So what is different then? The different one must be this one, NO2. So this is most likely a reduction of the nitro group. You remove the O2, the nitrogen lose the 2 oxygen, become O3, and then the nitrogen gain 2 hydrogen, it become H6 then. It become a phenylamine, as stated in the syllabus, reduction of the nitrobenzene by using thin and concentrated HCl. And then of course you need to add a base at the end in order to give you back the amine, so that, you know, because otherwise it will protonate when you just have concentrated hydrochloric acid. So here in step 1, this is reduction. That's the type of reaction. It's new in the syllabus in the sense that you have to add in the sodium hydroxide in the end to remove the HCl in excess. Yeah. So thin and concentrated HCl is very common. Acidic conditions, it will protonate to give you NH3 plus. That is why, in order to stop and get NH2 back again, afterwards, then number 2, you need to add excess NaOH to neutralize all the acid that you added. Okay, this is stated in the syllabus, in the 2022 syllabus. Obviously, back then they will accept just this, but nowadays you must have these as stated in the 2022 Cambridge syllabus, and that is pretty correct chemistry actually. So once you have this, you're gonna get T. T will react with S in the presence of NaOH to give you this. This thing here is called an azo group. So this is a coupling reaction. Coupling reaction in order to produce azo, to form azo compound. Azo compounds are brightly colored dyes that you are using colorings and stuff. So we know that we can see this bit here. This bit here comes from the phenylamine. The phenylamine just now. If you want to form azo, you must have the diazonium. So T must be diazonium. Diazonium is not a neutral molecule per se. It's actually a diazonium salt. So what you do is you convert the phenylamine into nitrogen, triple bond nitrogen, but nitrogen with 4 covalent bonds. If you count correctly, this nitrogen has triple covalent bond, 3 plus 1 is 4. This always exists as a salt. Do not show the nitrogen bonded to chlorine. Nitrogen in the second period element, 2s and 2p cannot form 5 covalent bond. It's a salt. It's a diazonium chloride salt. Okay, now this one will react with something else, and that something else is basically the phenolic site. So that thing there. But then we do it in the presence of a base, because this one will deprotonate phenol. Phenol is weakly acidic, and once it is deprotonated, it will be a much better nucleophile. So let me just draw this other thing first. So I am just following the answer at the bottom, the 2 benzene ring, and then the OH is there, and then I have SO3, and then this is minus, and then Na plus. Just follow the thing there. The nitrogens come from the diazonium, so this thing here is your substituted position. OH directs substitution at 2, 4 is being blocked, or 6. So it so happened that the product show you the 2 position rather than the 6 positions. It's okay, but it is part of that directing group. It's as given in the it's as given in the data booklet previously, but in the new syllabus, you're expected to know that activating groups directs at 2, 4, and 6 positions without relying on the data booklet so much now. Between these and these, they will come together in this coupling reaction, okay? And they will kick out a small molecule. You kick out the H plus, and this one kick out the Cl minus. You kick out the HCl reaction. Even though I call it a coupling reaction, the type of reaction is actually called condensation. Condensation reaction bring 2 molecules together and kick out a small molecule. Condensation is in the AS introductory chemistry under type of reaction. Coupling reactions is just the name of the reaction, but the type of reactions is the key focus in Introductory Organic Chemistry from AS. Suggest the structures, I did. Suggest the reagents and conditions for step 1. I did talk about the reduction of the nitro group, including the really important adding excess NaOH at the end, so that this one is basic, that you don't get the ammonium salt. You want to get back the phenylamine because you want to form the diazonium, so you must add excess NaOH at the end to neutralize all the hydrochloric acid that you have from that first step. So that first step there also have to reflux, and then second step, then you add excess NaOH. Okay. Now, as for the step number 2 was the formation of diazonium. So to form diazonium salt, formation of diazonium, you need something called NaNO2. This is called sodium nitrite. Nitrite is an O level or IGCSE level when you were 14 to 16 years old, chemistry type of content, NO2 minus, so Na plus NO2 minus, and this is mixed with dilute HCl. The dilute HCl and the NaNO2 will mix together and you will get HNO2. HNO2 is the nitrous acid or HONO. HNO2 is HONO, and that's the one that will convert the phenylamine to diazonium. And the reason you get a chloride salt is because you use dilute HCl there. But the conditions, now do not forget the conditions. It has to be kept cold around 0 to 10 degrees Celsius or 0 to 5 degrees Celsius will have been acceptable. Usually we just keep it in an ice bath to prevent the nitrogen from escaping as a nitrogen gas, which can happen very easily if you do this at room temperature. Next one, what type of organic salt is formed in step 2? In step 2, we get a diazonium salt. So it's just called a diazonium salt. What type of organic salt? Well, you get a diazonium salt. If you have to describe the family, it's R and then N, triple bond and then it's a chloride, where this thing is not directly bonded there because it's an ionic compound, giant ionic structure, the salt. Compound W has the following structure. Count the sigma and the pi. So if you think about the sigma here, you have 2 sigma. Carbon form 4 bonds, 1, 2. So there's 2 hydrogen there. There's 1 hydrogen there, 1 hydrogen, and there's 2 hydrogen there, so there's 2 sigma there. And then we have 3 sigma, so this is 1 sigma. This is 1 sigma plus 1 pi. There is 1 sigma there. This is a double bond. The double bond contains 1 sigma and 1 pi, just like this C double bond O. And we have 1 sigma there, and we have 1 sigma there. Now I'm going to look at the 2 hydrogen there, 1 hydrogen there, 1 hydrogen there, and well, I already talked about the 2 hydrogen there. That's why there's 2 sigma, single bond nitrogen, hydrogen, single bond nitrogen, hydrogen. Same thing with that. So what happened with these things which are in pink? These are single covalent bond to 2 hydrogens. So there's 2 sigma plus 2 is 4, 5, 6, 7, 8. So there's 8 sigma plus, there is 1, there is 2, there's 3, there's 4. And then there is another 2 more from this thing here, from the double bond, 1 sigma and 1 sigma. So there's 2 sigma. So altogether you have 12, 13, 14 sigma bonds. The pi bond is the easier one to count. There is just 1 pi bond there and another pi bond there. Altogether you get 16 covalent bond there. Just to double check, 2, 3, 4, 5, 6, 7, 8. Where am I? Hang on. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 sigma. And then the 2 pi bonds should be easy enough to count. Now the products of the reaction of W with cold HCl and also with this primary halogenoalkane, the carbon with the halogen is bonded to one other carbon. These products there are soluble in water but not in organic solvent. So soluble in water there means polar, so can form hydrogen bond with water, not in organic solvent. That's because organic solvent is non-polar. So what are we talking about? Structure of product. So W there is H2N and then double bond like this. what do we have here? We have amide, we have amide there, we have alkene, and we have amine. So amine are basic, amides are neutral. This is your amide, amides are neutral, and then you have your alkene chemistry. So what do we add here? This is an acid. So amides are neutral, will not react with acid. The HCl is, they say coal HCl. So this one here is, what do I say? It is not hydrogen chloride. Hydrogen chloride is a gas. But here they say coal HCl, so you could keep it coal because it is a solution. So this is referring to HCl aqueous coal. The fact that you use HCl aqueous, they will not do anything on the alkene because they are not pure HCl gas. So what we are doing really is H3N plus Cl minus. They will form a salt. They will form a salt. This is what I would expect to get. This is just your usual neutralization between the basic amine and the not carboxylic acid, and this acidic solution aqueous there, the coal HCl. So this will prevent the reaction of these as well. The reason why they use coal also is because the amide will only be hydrolyzed in the presence of hot acid. So you are not heating it up, the amide will remain as amide, which is why you get C4H9. So you have 1, 2, 3, 4, and you got 3 hydrogen, 4, 5, 6, 7, 8, 9. You got 2 nitrogen, you got 1 oxygen, you got Cl. Okay, so it follows that thing there. They are looking for the products and the structure. They don't mention skeletal or structural or display. I would rather do skeletal because there's elegance and that follows the nature of the question. You want to be fast and you want to be correct, so make sure you can do skeletal formula very, very well. This is a halogenol alkane, primary halogenol alkane, and we can see that there is Br there, so there must be some sort of substitution. They are looking for type of reaction, so they are not looking for mechanism, so do not write in nucleophilic substitution. Instead, type of reaction in AS chemistry. They don't ask you to confuse between substitution and nucleophilic substitution or electrophilic substitution. So don't get confused from your AS terminology, introductory organic chemistry syllabus type of reaction. So what we get there is your amine, your alkene, and your amide. Your amide wouldn't do anything there. Your alkene wouldn't do anything there. Your amine can act as a nucleophile. Just like when you have ammonia, it can replace these to give you amine. So what I can think about is I will get NH, and then I will get CH2, CH3, and I will get my other bit of the molecule. And if I think about this, I have Br. That is because, why do I have Br? Why do I have Br? Perhaps I have this, and then Br minus. Would that work? Let me think. 1, 2, 3, 4, 5, 6, C6, 3, CH3, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 2 nitrogen, and then I have 1 oxygen. So must be this molecule here. So I've just drawn a salt again. These are salts. They didn't mention, yes, they did mention soluble in water. So polar or salt. Salts are going to be ionic. Ionic salts can dissolve in water. Ion dipole bond, hydration of the cation and anions. So these are salts and they are soluble in water, and they follow this formula that have been given, and they follow the type of reactivity where this is just substitution. In fact, the NH2 there can act as a nucleophile based on the lone pair. We don't want the mechanism, we want the type of reaction there. Okay, hopefully that makes sense for that 3-mark question. That's the end of that 12-mark organic question there. So in this question number 9, this is actually part of the all syllabus. They used to have a section B on biochemistry. All of these are no longer relevant for this 2022 syllabus under the Cambridge International. In fact, it has been out since the 2016 revamp of the syllabus actually. So there's quite a lot of biochemistry in here. Used to be favorite among biology students. Obviously, these are no longer the favorites of people who don't do biology, and these are chemistry exams. So it's a very good thing that Cambridge has, shifted the focus of the chemistry exam to more chemistry and less biology. Anyway, there is a bit of NMR stuff in that particular question, and I thought it's actually quite nice to go through these particular questions. So this NMR spectrum of cysteine, we know that cysteine is an amino acid. So what happened is you got that NH2 and the CO2H. That is your basic amino group. And then you have the acidic carboxylic acid group. And these are still in the amino acids and protein chemistry in the current syllabus. And you have an R group and a H. This is how a general amino acid looks like. Your R group here is CH2SH. So I'm just going to put in the CH2SH. Now after we shake a solution of cysteine, so that means cysteine dissolved in water, with a few drops of D2O. We know the purpose of D2O is to do a fast exchange. This is as stated in the syllabus, obviously. Fast exchange of, I better separate out my fast and the exchange so that it looks better. Fast exchange of labile. Labile mean easily come off. So which ones are labile protons? OH and also NH are labile protons. You have NH there. You also have OH on the carboxylic acid end. So now your spectrum only shows 2 adsorptions because this and this will be gone by now as they are labile protons. So what happened then is what you see. Well, you will see the SH protons. And hang on, the NMR spectrum shows only 2 adsorptions. I wonder, why does it say only 2 absorptions? We know this and these are labile. Now there are 2 absorptions. So we have we have SH, we have CH2 and the H. I wonder if the SH is also labile protons because it started from 5 absorptions. Now you have lost 3 absorption because you only have 2 absorption now. Well, the only thing that doesn't make sense is the SH here, but let's see what's happening. If I have this very clear stuff, which is, let's say, A and B, if I add A, I will have 2 neighboring protons, so A will see a triplet because 2 neighboring protons, so therefore 2 plus 1 equal to 3 lines, so that is your triplet. Identify 2 types of proton responsible, so looks like A has to be this distinct adsorption E here, and F is a doublet. If I am here, assuming that SH, probably this one behave like OH, assuming, I am not entirely sure, but it seems like if when you are here you only see 1 neighboring protons because you don't couple to proton on OH. It seems like you also don't couple to the protons on the SH. So what happened there is you will have 1 neighboring protons because you only see these neighboring protons that you couple to. Coupling is this concept in NMR, which you don't do so much in A-level chemistry, but that is the origin of this splitting. So when it couples to these 1 neighboring protons, you will see 1 plus 1, there's your n plus 1 rule, and you will see 2 lines, and 2 lines represent a doublet. They are of equal intensity, 1:1, and this 1:2:1 intensity for this triplet. So it looks like that must be B there, and the SH is just another labile proton, just like NH and OH, although this is not technically in the syllabus, but the information very clearly shows that this must be labile as well. That's why you could do a fast exchange with D2O. So what are the 2 types of protons there? So A is going to be CH, CH2SH. This is where you are, and where you are, I'm going to underline it so that it is very clear I'm talking about where I am. And this is very common trick in more advanced NMR study, and usually this is what I teach my students. You must show the neighbor. If you don't show the neighbor, how would you know how many neighboring protons there are? Okay. Now to the other one, F is going to be this signal here. So again, we have CH, CH2SH. But now we are here with the 2 protons. We see 1 neighboring protons. We don't couple to that. Therefore, we see 1 plus 1, which is 2 lines and the doublet there. State and explain. So here there are 2 bits to it. You see there are 2 lines. Do not just explain. Do not just state. but state and also explain. For this signal or absorption at E, we see a triplet. This triplet is a 1:1:1 intensity. 1:2:1 intensity. And because this CH2SH, the one I underlined, will see it has two neighboring protons. So we talk about two neighboring protons. Therefore, 2 plus 1 equal to 3 lines, and 3 line is a triplet of 1:2:1 intensity. I'm pretty sure you won't get penalized without the intensity ratio, but I'm just telling you that's part of the Pascal triangle, which you have done in mathematics binomial expansion. Where was I? That was actually part of the previous question. There was the explanation. So now to the red color one. There is the doublet there. So we get a doublet for the other absorption because, well, the part 2 is the reason. So now I underline the CH2 of the SH, and then it sees, it has one neighboring protons. And when you have one neighboring proton, that is a singular, by the way, therefore you get 1 plus 1. The n is number of neighboring protons plus 1. Then you get 2 lines, and 2 lines will all be of equal intensity. That is your doublet of 1:1 intensity ratio. And that's the end of the NMR questions of these whole biochemistry questions. Very interesting question on NMR, especially on the fast exchange in the presence of D2O, where this labile proton disappear. But it turns out that this is also labile. It behaves just like OH or NH, although it's not really straightforward, like in your syllabus stated clearly, but you can very clearly indicate what is happening here based on the absorption as shown here. In this next question, we have aspartame is an artificial sweetener. So draw a circle, they want a circle, nothing else, around each chiral center. So when you have a carbon double bond, it cannot be chiral. And we're looking at this being a chiral center. So there is one group, there is this group with the ester, there's this group with the amide. There's a hydrogen not shown because carbon form 4 bonds, 1, 2, 3, there is one hydrogen there. This is the amide. This is not amide because this is not nitrogen. This is a carbon. It forms 4 bonds, 1, 2, 3, there's a hydrogen there. This is a CH2, this is a CH2. The benzene ring has no chiral carbon. The CH2 has no chiral carbon. Doubly bonded carbon has no chiral carbon. The CH3 has no other chiral carbon. So there are 2 chiral carbons there altogether. In the next one, in the stomach, aspartame is hydrolyzed by acid. So this is hydrolysis of acid, and you get 3 organic products. We need to be very careful because we have an ester. We also have an amide. The thing with an amide is they are formed from amino acid. Hang on, no, I better correct myself. Amides are not formed from amino acid unless you have proteins. Okay, I better correct myself. You have amide, but it's gonna break down to something that has NH2, and NH2 is basic or alkaline. You are in acidic hydrolysis, so this thing will not survive as NH2. They will protonate and give you the salt with the acid. We don't know what acid is being used, but we know every single acid contains H+, so we don't know what is the counter anions, but we know it must protonate using the lone pair and the nitrogens and give you some sort of ammonium kind of ion where the nitrogen form 4 covalent bonds. The active covalent bond needs H+ there, and you will have a positive charge on the nitrogen. So if I have to break the ester bond, this is the ester bond that I'm breaking. So they say use arrow to indicate the 2 bonds. So they don't want dash. I have to follow the question. Use arrow to indicate the 2 bonds. They would be hydrolyzed. The first one is the ester bond. So here, this is the arrow. This is part 2. And then the other bond that I am hydrolyzing must be this one here. Not this one because this is carbon. This is not nitrogen. This is a CONH. So this is the amide bond. Whereas this is the ester bond. Okay, so there's amide there. And this is the ester bond that you're hydrolyzing. Draw the structures of the 3 products after complete acid hydrolysis. We're going to get the alcohol, which is CH3OH. So if I just show H3C and then OH, that is from there. I'm now going to complete this site with the skeletal formula. This is going to give me the carboxylic acid component. And then this bit here is just bonded to a carbon, which is that carbon. It has a CH2 benzene ring. So I will just draw CH2 and then benzene ring, just like the question. And then on the other side, I have a NH, but this is amide. The amide will get hydrolyzed as well. I should get NH2, but I'm under acid hydrolysis. The amines are basic. The basic will protonate. I will not survive with a NH2. Instead, what I will get is NH3 plus. I do not have the anion because we don't know what acid it is, but every single acid contains H plus in solution. The very last thing here, this thing will get broken hydrolyzed because your amide get hydrolyzed, and this thing will give you the carboxylic acid. This is the amine. The amine is not further hydrolyzed, but it will also protonate to give you the salt. And then this is carboxylic acid. It will remain as carboxylic acid. So looking at your structure there, I will get a carboxylic acid there, and then I will get the amine. So let me just complete the other side first. What am I doing? This is carboxylic acid. So I'm just going to show that the amine is going to protonate. So there's NH3 plus. So that thing is going to protonate as well. And that thing, when you form the amine, is going to protonate like that. So I'm just going to copy paste that onto the space given. And those three are the organic products that we will expect to get after complete acid hydrolysis. Of course, when you write equations, you might get water being formed somewhere to balance the equation, but they want the organic products. So these are the three products that you get after you chop off or fragment the molecule upon hydrolysis. That is the ester bond, that is the ester bond, and this is the amide bond that you have broken or hydrolyzed. This next question, by referring to the structure of aspartame, so you have to talk about the structure, explain why it is soluble in water. Solubility in water could be due to ion dipole bond. That is usually the origin of the solubility of ionic compound. But then what you have here is a molecule. So typically we could also be thinking about hydrogen bond. This is the main focus here, not the ion dipole bond, because aspartame are not these products here. Aspartame is this whole thing here. So what we can see is this is ester. Ester cannot form hydrogen bond because there is no hydrogen bonded to the oxygen there. This is amide. You have a dipole there, but that cannot form hydrogen bond because the hydrogen is not bonded to the oxygen. This can form hydrogen bond. So the NH can form hydrogen bond. The OH can form hydrogen bond. We are looking at OH and the NH that can form hydrogen bond. So aspartame molecule has OH and also NH. Both can form hydrogen bond with water because we are talking about dissolving in water, right? Can form hydrogen bond with water molecule. Typically speaking, when we draw hydrogen bond, we have to write in the dipole. So I'm purposely showing the dipole here so that you can see that these are very polar bonds as characterized by hydrogen bonded to the very electronegative atoms like fluorine, oxygen, and nitrogen. But of course, here is just oxygen and nitrogen there. So I identified the groups, and the groups can form hydrogen bond with water molecule. There's my second point. But which group can form the hydrogen bond? That is why it was 2 marks there. Okay. Now this next bit is actually on nanoparticles. Nanoparticle used to be part of the old syllabus as this option topic called nanotechnology. It has been taken out from the curriculum actually. So you don't really need to do it, and I don't really need to do it anymore as they are no longer relevant starting from the 2016 syllabus. And since we are in 2022, there's actually a new modification to that 2016 syllabus, and this is still not in the syllabus anymore. Okay, that's the end of that, I should say 8 marks question because I didn't answer these questions. And that's the end of this tutorial essentially. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry on Facebook, Instagram, Twitter, and Telegram to get connected. And yeah, do consider upgrading to the silver tier membership on my channel so that you can get access to all the yearly paper tutorials. And of course, the idea is to continue supporting the work that I'm doing on the channel that will help a lot more people like yourself. Thank you for watching.